Hi, welcome back. In this video, I wanted to show you what happens if you don't tie down a payload as the truck begins to accelerate. And this is a great example of using multiple reference frames, where one of those reference frames where we actually create our equations of motion is a non-inertial reference frame, meaning that the accelerating truck, if you attach a coordinate system to it, that coordinate system has a non-zero change, a non-zero acceleration, and therefore it's non-inertial. In this example, we're going to look at what happens if you don't tie down a payload in a truck. So here the truck is going to hit the gas and accelerate this way, and we'll look at what happens to this block M as it starts to possibly slide off the truck like this. So I want to look at in this problem 335, it's just asking for what is the static coefficient of friction, what does it have to be for it to not slide off the back. I'm going to look at a worst case scenario where it actually does slide, and we'll say that our acceleration is 0.25 G's or 9.81 over 4. And it's going to accelerate for a time of 2 seconds. So the driver, he or she, hits the gas and accelerates for 2 seconds. And we're going to say it cannot slide more than 2 meters. So that gives us 6 feet of space that it can slide from here to here. 6 feet, or about 2 meters. When we're answering this question, if it's actually sliding, we're not looking at static friction. We're looking at a dynamic. What is dynamic friction there? Okay, our first step, figure out the equation of motion. We have this motion of the bigger truck and the motion of M, but here this acceleration is a kinematic constraint, so it's not a degree of freedom. We don't care how much force is required to move the truck at some acceleration A. We just know that the whole truck is moving that amount. So really all we have is just this back and forth motion X of this sliding block. So the sum of the forces in here, let's draw couple of coordinate systems. So we've got our mass M, and I'll give this its own body 1, body 2, so starting wherever it starts at some fixed reference, and then there's some global E1 and E2. So in this body reference frame, this is non-inertial. It has an acceleration. Our E, if we fix it to the ground, this is an inertial reference frame because our acceleration is 0. So when I talk about the acceleration of our mass, I have to have it with reference to O and then O prime. It's going to be equal to acceleration of our mass with respect to O prime plus the acceleration of O prime with respect to O. So our total acceleration is going to be some x double dot of B1 plus A B1. And here B1 and E1, because it's all parallel motion, they're equal. So this is also equal to x double dot plus A E1. We can use whichever unit vector we want. Now drawing our free body diagram, we have the weight of the object, we have a normal force. Our friction is actually pointing this way, this force of friction, and that's equal to our kinetic diagram of M times A M slash O, or M times x double dot plus A in that E1 direction. So mg equals N, and our force of friction for Coulomb friction is going to be equal to mu times N. So So that means we have this, our equation of motion is that mu mg is equal to m times x double dot plus our acceleration a. So the acceleration of the truck. Now I can plug in, let a equal g over 4, and I have that mu times g minus g over 4 equals x double dot. Now the best case scenario would be no acceleration. And if that's the case, then we can set these equal to 0. And this would be equal to mu g minus g over 4. So mu would be equal to 1/4. So for a quarter g, you would need a static coefficient of friction of 1/4 to make sure that the acceleration is 0. Let's look at a worst case. We want delta x, which is equal to negative x double dot over 2 times t squared, or that delta t is 2 seconds, so this is equal to negative 2 x double dot. We want our delta x max to be equal to negative 2 meters, which is negative 2 x double dot. So our x double dot max allowable is equal to this negative 1 meter per second squared. So now I've got a new x double dot is going to be, at best case scenario, 0, and in our worst case scenario, 1. And this is all meters per second. But x double dot I had solved for. This is also equal to mu g minus g over 4. So then I'll divide everything by g. So negative 1 over g is less than mu minus 1 over 4, which is less than or equal to 0. And then I'll add 1/4 to everything. So 1/4 minus 1 over g is less than or equal to mu, which is less than or equal to 1/4. This was the first term that we had found up above. And this is our minimum coefficient. 0.15 is less than or equal to mu, which is less than or equal to 0.25. So if we have a static coefficient friction of 0.25, then it won't move at all. If we have a dynamic coefficient of friction of 0.15, even if our static is 0.2, then it won't actually slide off the back of the truck. It'll move that 6 feet over to the back, and hopefully we can strap it down after that.